Thevenin theorem tells me that you can replace a complicated circuit by a simple voltage source connected in series with a resistor. And Norton tells me similarly that you can replace that circuit with a current source in parallel with a resistor. In this video, I want to focus on the procedure of finding these equivalencies. Specifically, I want to know, where did the 32 come from? Where did the 8 come from? How can I compute them? How can I calculate them? They're not random. Similarly, the 4 amps. So finding Thevenin or finding Norton is very, very similar. So I'll focus initially at Thevenin, and then I'll show you how we can find Norton. They're pretty much the same procedure. And frankly speaking, you can start by finding the Thevenin equivalent and then do a source transformation, or the opposite. You can find Norton and then do a source transformation to get Thevenin. All right, so let's get started. I'll start by finding first, I'll find the V Thevenin. So what I have in here is I'm basically replacing that big circuit with just a box, because the circuit doesn't matter. What matters is like, how does it affect, how do we replace it? So we're interested now in figuring out how I can replace this circuit with this particular pattern. I know it has to be a voltage source in series with a resistance. So I'll start by finding the V Thevenin. I'm going to call it VTH for V Thevenin. All right, so how can I find it? Well, first of all, usually we do the calculation in the original circuit, but what I can tell you is if you do the same type of calculation on the smaller circuit, you will end up with the same result. So what I'm really interested in is figuring out the V Thevenin. So let me take a look in here. How can I do that? Well, as it turns out, that the procedure is straightforward. So keep the port A and B open. So you're going to have what we call an open circuit. Okay, and frankly speaking, find the V of the open circuits. Basically, find the voltage of the open circuit at AB. Okay, well, let me just prove it to you. Well, if you write a KVL equation in here, you'll end up with negative V Thevenin. Okay, that's the voltage, plus, well, we know that there's no current because the circuit is open. There's no current flowing through the R Thevenin. So that means this is 0, plus V open circuit equals 0. That tells me that the open circuit is simply the same as the V Thevenin. So as it turns out to be, that if, in order for you to figure out what the Thevenin equivalent voltage is, what that V Thevenin is, just keep A and B open. Okay, and just figure out what the voltage across this A and B is. So let me go back to this circuit here. We know the answers already, but let me just show you how I calculated these answers. So here's the circuit that I've been using as an example. So what I'm interested in is the V Thevenin in here. There's no load at this point. I do not need to connect a load yet. So I'm trying to figure out the Thevenin equivalent. So I'm going to keep it at the open circuit. So what I will do is I'll call this here plus minus V open circuit. That's what I'm interested in. And all I have to do is just use any of the circuit analysis technique that I've seen so far just to compute that particular voltage. All right, so I'm taking a look at this circuit, and frankly speaking, if it is open circuit, that means this resistance in here it's there, but there's no current through it, so that's a 0. So the V open circuit is simply the same as the voltage in here. If I write a nodal equation, if I put my reference in here, that will be my V open circuit actually. Okay. Again, the reason why it will be the same, because this is the voltage across the current source in here, and it is the same voltage across it from here, because there's no current going through this part, because this is an open circuit, so there's no current flowing from here. All right, so all I have to do is just write one nodal equation in here, and so let me just do that. So that will be V open circuit minus 25 divided by 5 plus V open circuit divided by 20 minus 3 amp equals 0, and that should give you a V open circuit, hopefully of 32 volts, as we've seen before. So now we were able to find the V Thevenin. So now we know that this one here is now 32 volts for that particular example circuit that we'll be dealing with. Good. All right, so now what we need to do is we need to figure out the R Thevenin. And as it turns out, that there are 3 methods to find this R Thevenin, depending on the original circuit and how it looks like. I'm going to start with the simplest case in here. Again, I'm going to take a look at the equivalent, just do all the calculations over there, and just transfer that method to the original circuit and the example I'm going to show you. Okay. So, well, method 1 tells me that if you only have just independent sources, so all the sources you've seen are independent in this particular circuit in here, what you can do is simply, well, just turn off these independent sources. By turning off the independent sources, let me show you that the equivalent circuit in here, A and B, and taking a look at the R equivalent that you see in here, you will end up with R Thevenin. And you can see it directly from this simple circuit that if I just see what the R equivalent, it's just simply R Thevenin. So just turn off the independent sources, figure out the R equivalent from the port AB, you'll end up with the R Thevenin. So let me go back to this particular example in here and let's do this here. So how do I turn off the sources? Well, depending on whether it's a current source or a voltage source, of course, a voltage source will be replaced by a wire, a short circuit, because I'm interested in the V equals 0, and a V equals 0 is typically across a wire. Okay, so we do that, and we keep the 5 ohms in here, and we keep the 20 ohms in here. And what about the current source? Well, a current source, you basically open it by just open circuit, so there's nothing in there, and then we keep that 4 ohms in here. So when we computed the V Thevenin, we said the 4 ohm does not exist because there's no current through it. In here, it's not a circuit. We're finding the equivalent resistance that we can see from here. So the equivalent resistance that we see from here is the R Thevenin. So, and that should be, R Thevenin is just simply 5 in parallel with the 20. So if you see it, these ones in here, they share this node, they share this node, so the 5 and the 20 are in parallel, plus the 4 ohm, because the resulting resistance will be in series with the 4, and that will be the R Thevenin or the R equivalent, and you can do this calculation and you'll end up with 8 ohms. Okay, so the Thevenin equivalent resistance is just simply 8 ohms. So this is method 1, and this is exactly what I've seen before. So I gave you that should be plus 32 volts in connection with an 8 ohms. That's how I found them. Alright, so let me just show you a different method to compute R Thevenin, and I'm showing you different methods because different circuits will require you to use different techniques. For example, what if the circuit that I had here has some sort of a dependent source? If it has a dependent source, we can't turn off a dependent source, so method 1 would not apply. So what about method 2? Well, method 2 tells me, okay, why don't you just do the following? Connect A to B, basically short circuited, and figure out what the current flowing through it is. So we know, basically just figure out what the I short circuit is. Okay, and the R Thevenin in that particular case will be simply, well, using Ohm's law. It's V Thevenin divided by I short circuit. That's what it would be. Okay, and of course we know that V Thevenin is just simply V open circuit because this is what we saw. So V open circuit divided by I short circuit. So pretty much the procedure is as follows. Let me go back to the same example that we've solved before, and I'm going to tell you here's the deal. What you do is you just basically connect the ports together, you basically short them, and I'm going to tell you, let's compute the I short circuit in here. And you can use any analysis technique that you want to figure out what that current, that mesh. You can use mesh, nodal, whichever you prefer. I'm going to go in here and I'm going to say, you know what, I'll use nodal analysis again. So I'll put here, because this is basically a voltage, I'm just going to call it V, because that I short circuit will be simply V divided by 4. Okay, so that nodal analysis will be V minus 25 divided by 5 plus V divided by 20 minus 3 plus V divided by 4 equals 0. And again, this is not open circuit, so that 4 actually has some current in it. So I have to incorporate it, and you'll figure out what the value of V is, and that should be, I found that answer to be V is just simply 16 volts. Okay, V is 16 volts. I short circuit is simply 16 volts divided by 4, which is just 4 amps. Okay, so we know that now. So based on the rule, remember, it's like we found what V Thevenin is. We found that V Thevenin happened to be 32 volts. Okay, and what I'm interested in is the R Thevenin, which I don't know what it is, but I know the short circuit. So R Thevenin is just simply V open circuit or V Thevenin, either way, divided by I short circuit. Okay, and that happened to be 32 divided by 4, and that should be 8 ohms. And that's exactly the same number that we found using method 1. So method 2 just basically short circuit like method 1 just turn off all the sources if they're all independent. Method 2 tells me, well, if you have a mixture of independent and dependent sources. Frankly speaking, it applies also if you only have independent sources. Just short circuit it, figure out what that the current, and just divide them by V open circuit divided by short circuit. The third method to find the R Thevenin is probably the most involved one, but it's necessary because it's the most generic one. In the previous two cases applies to dependent and independent sources together. So this particular case applies to pretty much any combination of sources. And specifically, it applies to the case when we have only dependent sources. Let's assume that that circuit here has no independent source. Everything is dependent. Method 3 is the only one you will be able to do. Okay, so let me walk you through it. So what does method 3 tells me? Well, method 3 tells me that what you need to do is first turn off all the independent sources. So if you have dependent sources, you can't turn them off, but the independent sources, the ones that we represent as circles, we just turn them off. So I just did this here for this particular circuit. Turning off a voltage source is just simply replacing it with a wire. Our Thevenin stays the same, and then what it tells me is the following, that you need to go in here and you connect what we call a test source, and that source could be voltage or current. It does not matter, whichever you prefer, and I'm going to call it VT for test, and you can give it a specific value, for example 1 volt, 2 volts, whatever value you want. And what this method tells me is you need to compute what the test current, if it's a voltage source, you compute the test current. If it's a current source, you compute the voltage across it. Okay, and you compute that, and our Thevenin becomes simply, and you can probably see it, it's just simply Ohm's law in this particular case. Our Thevenin is just simply V test divided by I test. So typically you give V test some sort of a value, and you tell me what the I test, and you compute the I test, and you just divide them by each other, and you get the R Thevenin. Or if you have it as a current source, you know what this is, you compute the VT, and you divide them by each other, and you get that particular value. So let me go back to the example we've been dealing with, and let me just do that exact thing. So what I will do is I'll turn off all the independent voltage sources and current sources. So I'm going to turn off that 25 volts, making it into a 0, which is a wire. And then I have a resistor in here. Let me just redraw that. Okay, and that's 20 ohms. We keep it. And now here we're going to turn off this current source, and we're going to do 4 ohms in here. The current source, we just replace it with the with just an open circuit. And now I'm going to connect a voltage or a current source. It's up to you, whatever you want to connect. I'm going to connect a test source. I'm going to call it VT, and I'm going to make it 1 volt. You can give it any value, just 1 is just simple. What we need to do is figure out what IT is, what the test current is, and we just have to divide them by each other. So simply we can take a look at this. What I'm interested in is figuring out the IT. Well, I can replace these values in here and figure out what the is for, and the way we can do it is maybe we can, I mean, if I combine these two resistors and that, I won't lose the I of t. So I can replace this circuit with simply some sort of a resistor in here, and that resistor will be 5 in parallel with the 20 plus 4, which we have seen to be equal 8 ohms before, because this is how we use method 1. Method 1 was like just equivalent. In this particular case, I don't have dependent sources. That's why I can use method 1. But if I had a dependent source, I wouldn't have been able to do this because I can't turn them off. So in that particular case, I would have had to do this here and compute that V of t. Well, not the V of t, the I of t in here. And hopefully you have seen it by now that that I of t will be simply 1 divided by 8. Okay, so now what would be the value of R Thevenin? Well, the value of R Thevenin is just simply V test divided by I of test, and that will be, the V test is 1 divided by 1 divided by 1, 8, and that's just simply is 8 ohms, and that's basically the R Thevenin that we found in the other 3 methods. So in summary, to find the Thevenin equivalent of a circuit, you need to find 2 things. You need to find the voltage source value, which we call V Thevenin, and you also want to find the R Thevenin, which is a Thevenin equivalent resistance. And the way we do it is summarized here on these steps. So the first thing you do is you take whatever circuit you have, no matter how complicated it is, you take, you open circuit it wherever you want to find the Thevenin equivalent from, and you compute the V open circuit. That V open circuit will be your Thevenin equivalent voltage. All right, and then Thevenin, for the R Thevenin, you have options. You have 1 of 3 methods. So in the most simple case where all sources inside that complicated circuit happen to be independent, basically these circles, current and voltage sources, all you have to do is just turn them off, figure out the R equivalent, and you're done. That will be your R Thevenin. Now, if you had a mixture of dependent, independent, or even the independent, it will apply to the independent, but really, frankly speaking, method 1 is much simpler. But anyway, if you have a mixture of independent and dependent circuits, what you need to do is you will go to that particular circuit that we started with in here, and instead of open circuit, what you do is you short circuit the output here between A and B, and you compute the I short circuit. And by computing the I short circuit, you divide them by each other, you'll get the value of R Thevenin. And the last method, which is method 3, frankly speaking, it applies to all sorts of circuits, but it's mostly important because it applies to circuits that contains dependent sources only. So the previous methods here, like if you have a mixture of them, that's good. If you have independent, that's good. So if you have dependent sources only, you will not be able to use method 2 or method 1. Okay, so you have to use method 3. So method 3, what it tells you is, instead of having open circuit and short circuit, what you will do is you go in here and you connect what we call a test source. And that test source could be a current or a voltage source, it doesn't matter. You will specify the value of that test source and you compute the opposite. So if it happened to be a voltage source, a voltage test source, you compute the current leaving it. If it happened to be a current source, you compute the voltage across it. And you divide those two values by each other and you'll get the R Thevenin. Now, if you want Norton equivalent, well, it's straightforward implementation of source transformation. You can find the voltage or the Thevenin or the Thevenin equivalent, do source transformation and get the IN. But also you can technically go directly and find the Norton equivalent without having to go through the Thevenin and do the source transformation to get the Thevenin. So the way we find R Norton is the same as the way we found R Thevenin because they're exactly equivalent, one of the three methods. But what about I Norton? Well, I Norton can be found really shortly. So instead of having to start with an open circuit, in the case where you have Norton, you'll have a complicated circuit. What you do is the first thing you do is actually you short circuit. And let me show you why. Because if you short circuit this particular circuit from here, that will be the I short circuit. You're effectively short circuiting the RN. And you're effectively telling me the I short circuit is just simply the I Norton. So by computing that, by short circuiting the circuit from A and B, you'll basically compute the I Norton. And you go in here, basically here's the step summarized just for finding Norton. So you start with the short circuit instead of the open circuit, and the rest are just updated to do that. Turn off all the sources, figure out the R equivalent. It's the same as before. Method 2, well, I know the I short circuit, so in this particular case, instead of having to find the short circuit, we need to find the V open circuit. Okay, so we just swapped them for finding Norton. Method 3 is still the same. You turn off all the independent sources, and then you connect the test source and you divide the values by each other, and you'll get the value for R Thevenin.